Hey guys, it's chapter 3, the beginning of understanding elements and their properties and how we can make compounds with these elements and their bonding. So, pretty important chapter, especially understanding how elements compare to each other and their properties, and where they're on the periodic table depends on their properties as well. So, first thing is classifying elements, the periodic table. So first person who's considered the father of the periodic table is Dmitry Mendeleev, and yes, he has his own element named after him. He based the table based on their atomic mass. So he basically put them in order by their mass. And this was the original periodic table. You can see really closely there's helium there, lithium, sodium, potassium, all those very similar that we know today, beryllium, magnesium down, boron, aluminum. So he started something, and he actually had holes in there that he predicted to other elements. He proved that the missing atoms can be predicted, and he basically was the start of organizing our elements. This is our current periodic table. So very different what he did, but you could see where it started. You have lithium, potassium, and sodium over here, beryllium, magnesium, boron, and aluminum. So he did start something very important to science. Here we have the metals. So this staircase here basically separates the metals and the nonmetals, and then what we have here are called metalloids. Okay. Now the nonmetals are over here to the right of that staircase. We move the staircase a little bit because these are not exactly nonmetals. Okay. So in between these purple elements, we call those metalloids because they have both properties of metals and nonmetals. So they can be conductive, and they can also have low melting points. They can be brittle, but also have high melting points. So they have different type of properties that we call the mixture between metals and nonmetals, the metalloids. Okay, we have columns and groups. So the columns and groups are the families. That's the up and down. And then we have periods, which are called the rows, and those are just the number of their energy levels. So we talked about that earlier this year. Here are some properties of metals and nonmetals. So metals have, they mostly vary in color, but mostly silver, maybe black. They are solids, except mercury. Nonmetals could be anything from liquids, solids, and gases at room temperature. They have low melting points and boiling points. So usually solid at room temperature, hard and dense, good conductors of electricity. They have good conductors of heat. Malleable and ductile, which means they can be shaped and drawn into wire. And they're mostly gray in color. So solid, dense, hard, good conductors of heat and electricity. They can be shaped and gray. Nonmetals, they can be anything. They have liquid, solids, and gases at all room temperature, where like bromine is a liquid, but chlorine is a gas, iodine is a solid. So you can see you have different phases. They are softer than metals with low densities. They're poor conductors but good insulators, meaning they can be used as ceramics. They do not transfer heat very well. They're brittle, meaning they will break when you try to bend them or even like hit them with a hammer. And they vary in color. So lots of different colors with nonmetals. They have yellow, orange, black, green. So the yellow is green, and so you can see they have different varying colors. Metalloids have both properties of the metals and nonmetals. They aren't great conductors of heat or electricity. but they sometimes can be brittle, but also malleable. They're gray in color. Here's silicon. Silicon's a great conductor, not a great conductor, it's a good conductor, but not of heat. So that's why it's used in computer chips. Here we have boron. Boron's more brittle than silicon. It's used in doping of electric solar cells. Here we have antimony. Again, gray in color. All right, the transition metals. So these are the metals between the metals and the non-metals, so they're called transition metals. Notice the elements in the columns, they all have the same valence outer shell. So we talked about this previously, that group 1 all have one, show it here, one electron in the outer ring. So all have one in the valence shell, where beryllium, magnesium, and calcium all have two because it's in group 2. Boron all have 3 because they're in group 3. Carbon group has all 4 in the valence shell. The nitrogen group all has 5. Oxygen group all has 6. And 7 for the halogen group. And the noble gases all have 8 except helium, because helium can only hold 2 electrons. So that's why it doesn't have 8. Alright, this goes back to Mendeleev's table. He had very different elements. So he put, like, for example, potassium, which is very reactive, and copper in the same group. So you can see that why it wasn't really going to be a good fit. Copper is very stable, where potassium is not. 40 years later, Moseley, he rearranged the elements by their atomic number, which gave the table better periodicity. So here's Mr. Moseley. In 1915, he arranged it with them having same properties within the group. This is the short form table. So the reason why it's short form, so it fits better, because if you put the, they call these the actinide and lanthanide series, you put these down here, it makes the table very long. So that's why they short form. All right, periods, again, we talked about that. It goes horizontal. These all have the same number of energy levels. So if it's group 5, they have 5 rings or 5 energy levels. Okay, group 4 has 4. The groups, the families, they're up and down. They run vertically. So all these have the same valence electrons and similar properties. So in group 1, or let's say group 7 here, that's the halogen group. They all have 7 valence electrons, and they all have similar properties, meaning they are very reactive, and we'll get to that reason why later. All right, first group, group 1, alkali metals, lithium, sodium, potassium, rubidium, cesium, and francium. These are the most reactive metals. Okay, they all have 1 valence electron. Where the most reactive elements and metals, are your cesium and francium. They all have 1 valence electron and very explosive. They will react with water to produce hydrogen gas and explode. Alkali earth metals, group 2. These are a little less reactive than the alkali metals, but they're still reactive, meaning they will be in place in water. They will make hydrogen gas and explode, especially strontium, barium, and radium. As you go down, they get more reactive. The higher ones do not, are less reactive. Transition metals, you can see here, most of them are pretty gray, but you have gold, obviously gold color. You have copper, which is a bronze color. Most of them are silver and gray, and these are used for different sources. So you can see, like, iron is more brownish red. Here's silver, obviously silver color. Here's tungsten, very strong metal. Titanium is very strong metal. So they're very strong. but also could be radioactive, so like uranium, plutonium down in the bottom. All right, the boron family. This is group 3A. They all have 3 valence electrons. Boron's only metalloid here. The rest of them are just metals. Group 4, or the carbon group. This contains a wide variety of elements where you have carbon to be a non-metal, so like diamond and graphite. 2 metalloids, silicon and gallium, and then 2 metals, lead and tin. So it's a very wide range of different type of elements here. And they'll have 4 valence electrons. Nitrogen group. Nitrogen, phosphorus, acetine, antimony, and bismuth. Again, it has some nonmetals, and which is nitrogen and phosphorus. You have metalloids like acetine and antimony, and then a metal, bismuth. Oxygen group. Oxygen, sulfur, selenium, tellurium, and polonium all have 6 valence electrons normally. And then you have the halogen group, very reactive, the most reactive nonmetals, which is starting with fluorine is the most reactive nonmetal. And then as you go down, iodine and acetine are the less reactive nonmetals. So they're opposites of metals, where the most reactive metals are near the bottom, the most reactive nonmetals are on the top. And the most non-reactive group is the halogen group the noble gas group. These are called noble gases for a reason because they are inert, meaning they don't react, non-reactive gases. These are your typical, we know what helium does, we've seen neon lights, radon you've probably heard of, which is a poisonous gas. So all these are gases, they all have 8 valence electrons, and the reason why they're non-reactive because they have 8 valence electrons. All right, metallic properties we talked about mostly having in silver color. They have luster, I mean they shine. They're solid at room temperature except mercury. They have high densities. They are malleable and ductile, good conductors of heat. Atoms have between 1 to 3 valence electrons. Atoms are loosely held onto their valence electrons, meaning they will give them up easily. And that's important to understand, that these atoms will lose their electrons. And they will rust, meaning they will oxidize with oxygen. All right, periodic trends. So these are important to have on your table. So on your periodic table, you want to make sure you have understand the properties. So the more metallic ones are on the bottom, the less metallic are to the right. Atomic radius. So the radius is obviously from the nucleus to the outer electrons. There's 2 determining factors, the number of protons and the number of energy levels, that will determine the size of the radius. So as you are starting to gain more protons and more valence electrons, so as you go across the period, okay, atoms are gaining protons and they're gaining the electrons in the same level. So as you bring in more protons, you're pulling in those electrons. So the radius is getting smaller as you go across the period. So you can see here, hydrogen has 1 proton, 1 electron. Helium has 2, and it gets smaller. Here, lithium has 3 protons and 3 electrons, and again will grow smaller. So once you get to 4 and 4, it will just keep bringing them in. Now if you go down the group, you're going to get bigger. This is pretty easy because as you go down, the energy levels are growing. So if you have more levels, more shells, you're going to have a bigger group. So it's like an onion. You have more levels of an onion, it's going to be a bigger onion. So you can see here as you go this way across the period, it gets smaller, and as you go down, it gets bigger. Okay, smaller across, bigger down. All right, atomic radii versus atomic number. You can see here also, as you go down the group, lithium to neon. So lithium is here. Going down, the radius is getting smaller. But you look at lithium and sodium, it's getting bigger. Okay, going up. All right, electronegativity and ionization energy. So electronegativity is the wanting of electrons. Ionization energy is the removal of electrons. So the electronegativity is the ability to attract an electron to itself, where ionization energy is the required to remove electron from the atom. Electronegativity, everything points towards fluorine. The most electronegative atom is fluorine. So as you go further away from fluorine, the less electronegative it is. If you get closer to fluorine, the more electronegative it is. Here's ionization energy. So you can see the general trend. Look at period 2, lithium, the ionization energy is increasing as you go towards the noble gas. There are some bumps, and that's past the scope of this class, but there are some bumps in the road that decrease a little bit, but general trend is an increase as you go across the period. Now if you look at the down the group, helium, neon, argon is going down. So ionization goes down as you go down the group, and as you go across the period, it goes up. Valence electrons versus atomic number. Obviously, the more as you go across the period, the more valence electrons you got. Pretty simple on that one. All right. Alkali metals versus atomic radii. So as you're going down the group, lithium, sodium, potassium, rubidium, cesium, the radius is going up, which makes sense because you're increasing the number of shells, energy levels. Ionization energy is going down. So the reason why ionization energy goes down, because since there's more energy levels, there's more rings, the distance between the outer electron and the nucleus is getting further and further apart. So it means if you're further and further apart, the less energy required to remove that electron. So the ionization energy is lower as you get a bigger radius or a bigger shell. All right, chemical reactivity down the group. So again, as you go down the alkali metals, you are going to have a weaker hold onto their electrons. So it means there's a greater chemical reactivity. So the weaker hold onto their electrons means a greater activity. That's for metals though. So you can see here, metal activity as you go to the left and down. Francium and cesium are down here. For non-metals, the most reactive is fluorine, so they're opposites. So if you remember where fluorine is, you remember where francium is, you can figure out chemical reactivity. Non-metals are going to be towards fluorine, being more active, where metals are more active with francium. Most reactive fluorine for non-metals. All right, so just a quick sum up. As you go down the group, okay, the metallic properties increase, energy levels increase, atomic radius increases. Those three things. As you go to the right towards the nonmetals, atomic radius decreases, valence electrons are increasing, metallic properties are decreasing, and ionization energy is increasing. Daddy? Yes. All right. So metallic properties increase, energy levels increase, and atomic radii increases as you go down. As you go across, atomic radii decreases, valence electrons are increasing, metallic properties are decreasing, and ionization energy is increasing.